Welcome to Tech channel. Today we are going to discuss a bullet point for the competitive exams like Tggenco, Transco, Sccl, GATE, and Singareni exams. Let's go for the topic data converters, digital to analog converter. Here it is digital to analog converter. The resolution formula is equal to step size by FSO into 100. The percentage of resolution is equal to 1 by 2n minus 1 into 100, where FSO is equal to 2 power of n minus 1 into step size. Here you can see the R2R method. The FSO is equal to voltage regulation minus weight of LSB, where VR is the VR minus VR by 8. This is R2R method. Now we can go for the analog to digital converter. This converter time is equal to n dot t. The 3-bit flash type analog to digital converter is also called as parallel analog to digital converter. The accuracy is poor. Here the accuracy is poor. Dual slope of analog to digital converter, where V output is equal to minus V by RC into time. It is very accurate, it is very slow in conversion process. Dual slope analog to digital converter is very accurate, but it is very slow and it is in conversion process. When damping ratio increases, the stability increases. This is the important point. Whenever the damping ratio increases, the stability increases. This comes under these control systems, where these damping is equal to 0, that is undamped. It is when zeta is equal to 0, it is undamped. The roots are real and imaginary. Whenever the zeta is equal to 0, it is undamped. Roots are real and imaginary. Zeta 0 less than zeta less than 1 underdamped, it is underdamped. The roots are complex and conjugate. Where zeta is equal to 1, critical damping. The roots are real and equal. Zeta greater than 1, it is overdamping. Roots are real and unequal. Where zeta increases, the stability decreases. The time constant is equal to T is equal to 1 by zeta in omega n, where omega n is equal to damping frequency. Now we can see that critical damping, C of t is equal to 1 minus zeta omega n t by under root of 1 minus zeta square sine omega dt plus pi, where zeta is equal to 0. Whenever the zeta is equal to 0, it should be 1 minus cos omega n t. The transient response parameters. Delay time is equal to 1 plus 0.7 zeta by omega n. It is delay time. 50% of the final value it is. Next, raise time. Raise time is TR. Raise time TR. The raise time from 0 to 100% its final steady state, where TR is equal to pi minus zeta omega d. Peak time TP, where TP is the peak time, TP is equal to pi by omega d, which is equal to 2 pi by omega d when t is equal to 2p. Peak overshoot, that is MP. Peak overshoot, that is MP. MP is equal to A e power of minus zeta pi by 1 minus zeta square, where this peak overshoot is inversely proportional to zeta square. Settling time TS plus or minus 5%. The settling time is equal to 3 by zeta omega n. When it is 2%, TS is equal to 2 by zeta omega n. In exams, maximum get problems on these things. Any one of these transient response, you can get a formula. They have some shortcuts on this. I can discuss in some other videos. Here we can see that if zeta increases, that is damping ratio increases, the raising time increases, the peak time increases, and peak overshoot decreases, damping frequency decreases, and stability increases. The number of oscillations is equal to where Ts settling time, where Ts is equal to settling time by 2 into peak time. Steady state errors. Here you can see the steady state errors. Kp, that is Ts, z of s into h of s, where limit extends to s tends to 0. Here s tends to infinity, s tends to 0, a by g of s plus h of s, where kv, limit s tends to 0, s of g of s, h of s. Here you can see s, when kp is equal to limit s tends to 0, s square, it is parabola, it is no, kp is a parabola, kv is a ramp, and kp is a steady state. This error is equal to ess is equal to a by 1 plus kp, where ess is equal to a by kv, ess is equal to a by kp. These are the formulas, they are the formulas, you can remember it. Based on these formulas you can get problems in competitive exams. If a system increases, the error decreases. If the type of the system increases, the error decreases, accuracy increases, and stability decreases. PD controller PD controller improves the stability, decreasing the damping ratio. In this PD controller, the bandwidth increases, raise time decreases. Whenever the bandwidth increases, the raise time decreases. The speed increases, transient response increases. Whenever the speed increases in PD controller, the transient response also increases. Here you can see that G of S is equal to Kp plus Kds, where Kp 1 plus TDS. PI controller, these all comes under the control system. This PI controller G of S is equal to Kp plus Ki by S, which is equal to Kp plus 1 by T of S. The steady state error decreases. Here the steady state error decreases, bandwidth decreases. Here steady state error decreases, the bandwidth decreases, raising time increases, steady state response increases, speed decreases, and transient response decreases. Here you can go for the PID controller. G of S is equal to K1 plus 1 by Ts plus TDS. The root locus diagram, the centroid is equal to sum of P minus sum of Z P minus Z, where P is equal to poles, Z is equal to zeros, P minus Z poles minus zeros. The angle of azimuth theta 1 is equal to 2L plus 1 pi by P minus Z, where P minus Z equal to 1 and L is equal to 0, 1, 2, 3. If P minus Z is equal to 0, no angle of azimuth required. The gain margin GM in decibels, 20 log 1 by G of j omega pi plus G of j omega into H of j omega, where G of j omega H of j omega pi is a phase crossover frequency, which is equal to minus 180 degrees. If j omega pi does not exist, the gain margin is infinity. 1 minus is 1 minus 1 by 0, which is equal to infinity. The gain of the system increases, gain margin decreases. Here you can see that gain of the system increases, gain margin decreases. The gain of the system is inversely proportional to the gain margin. Here you can see the phase margin. Phase margin. This phase margin is equal to 180 minus G of JW plus H of JW, where W is equal to WG, that is grain crossover frequency. Gain margin and phase margin are the relative stability. Gain margin and phase margin are relative stability. The resonant frequency WR is equal to WN under root of 1 minus 2 zeta square, which is equal to 0 less than or equal to zeta less than or equal to 1, where omega r, that is resonant frequency, less than omega d. The zeta should be in between the 0 greater than or equal to 1 by root 2. Resonant peak, that is mr, equal to 1 by 2 zeta under root of 1 minus zeta square. Whenever these resonant peak is infinity, zeta is equal to 0. Whenever the resonant peak is 100%, then zeta is equal to 1. These are the most important one, which is asked in different competitive exams. Whenever the zeta increases, the resonant peak decreases. Why? Because it is inversely proportional. Whenever the zeta greater than or equal to 1 by root 2, these resonant peak should be 1. Here you can see the bandwidth formula. Bandwidth is equal to resonant frequency under root of 1 minus 2 zeta square plus 1 minus 2 zeta square plus 1. Here you can see the zeta increases, that is damping ratio increases, the resonant frequency decreases, resonant peak decreases, bandwidth decreases, raising time increases. Next, resonant frequency decreases, WD decreases, and stability increases. Initial and final slope of the Bode plot. The initial slope is equal to n into number of integrals n into 20 dB. The final slope is equal to p minus z whole minus 0 minus 20. The Bode plot slope is equal to 20 log 2 power of k minus n into 20 log wn, that is equal to damping frequency. Omega d is equal to damping frequency. Here you can see the formula 2 power of minus 1, which is equal to 6 dB. It is also 20. 2 power of minus 2 equal to 12 dB. It is also, you can write as 40 dB. 2 power of minus 3 is equal to 18 dB. You can write as 60 dB. You can see in Bode plot. You can understand whenever see the Bode plot how it should be. It is just formulas for shortcuts you remember for exam purpose. Phase plot. Phase plot is equal to under G of S H of S, which is equal to minus 90 plus tan inverse W by 2 plus tan inverse omega by 4 W by 4. The minimum phase system, poles and zeros will not be on right side of S plane. Minimum phase system, it is also important. Minimum phase system, poles and zeros with not lies right hand side of the S plane. G of S H of S is equal to P minus Z minus 90. Non-minimum phase system, here this is minimum phase system, it is non-minimum phase system. Poles and zeros will be lies on right hand side. Here not lies on the right hand side, here lies on right hand side. All path system, G of S H of S is equal to 1 minus A T of S by 1 plus A T of S. From this, maximum control system formulas are completed. Next we can go for the further video.